All right, now we're on to pit number 20. On number 20, we have basically a rod that hangs like this. There's a mass of 2 kilograms, a length of 2. There's a 2.6 kilogram mass here. And 0.4 meters from the end. There's a string. Makes 53 degrees there. Okay, that means we got a downward force here. This side. That's 53. All the angles are going to be 53. All right, so there's some torques on it. Now, let's see. This left-hand side, from the point of rotation, has got to be equal to the torque of the right-hand side of the rod plus the torque of that weight. Now, there's about, since it's 0.4 from one end of a 2-meter rod, that's about 20%. So there's 20% on this side and 80% of the rod on that side. So the left-hand side would be about 80%, 0.8 times the mass of 2 times 9.8 times the distance from point of rotation, which is about 0.8. That's to the center of mass again, times the sine of 53. That's got to be equal to, or that would be the torque of the left-hand side. They don't have to be equal. I should say that. We're trying to find the net torque on there. We're going to see if it's rotating or not. So that's got to be equal to the torque on the left-hand side. The total torque on the right-hand side is going to be, again, about 20% of the mass of 2 times 9.8 times the distance to the point of center mass, which is 0.2, times the sine of 53, plus the weight itself, which is 2.6. It's 0.4 meters from the point of rotation. 9.8 makes it times sine of 53. Gives me a total torque on this side of 8.76. Now the total torque on the other side is 10. So that means I've got a net torque of 1.24 Newton meters, making it rotate in a counterclockwise direction as I've got it drawn. Now, the second part asks what happens to the angular acceleration as it rotates up. Well, it reaches a maximum because the maximum amount of torque is going to be at 90 degrees. So once it is horizontal, it's going to be at its maximum acceleration. Then it's going to actually slow down as it goes the rest of the way. The last one, we have a catapult. Now, if we look at the catapult in a horizontal position like they tell us to, there's the ballast over here. There's the point of rotation. There is the guys pulling down on it. There's the weight pulling down on it. There's the massive beam itself pulling down in this direction. There's also the bit of the beam sticking out in that direction. These two cause it to rotate this way. These three cause it to rotate that way. What we want to do is we want to figure out the mass of that balance. So all the torques have to be equal. So the torque of the missile out here would be its mass times 9.8, which makes it its force, times the distance to the point of rotation, 3.5. It's horizontal, so the sine is going to be 90, so we can throw that out. We know that the prisoners are exerting a force of 550 newtons 2.6 meters from the point of rotation. And the beam itself, we've got about 0.875% of it on the left-hand side. So that's times its mass times 9.8. That would be the force on the left-hand side. Times the distance to the point of rotation, 1.75. That's the distance to the point of the center of mass. That's got to be equal to I've got about 12.5% or 0.125 of the beam. It's 200 kilogram mass times 9.8. On the right-hand side, distance to the point of the center of mass is 0.25 plus the mass of my ballast times 9.8 times its distance of 0.5. So I basically know everything except the mass of that ballast. I do my algebra. The mass of that ballast is going to be about 1,400 kilograms. It's got to be pretty big because it's on a very short end of the lever. Now we want to figure out the total force on the horizontal support. That's the horizontal support that's keeping that thing, it's on the pivot point, it would be a better way of saying it maybe. Well, the total forces on it would be the mass of 75 times 9.8, taking all the downward forces and add them up. 550, that's a downward force. The beam itself is 200 times 9.8. The ballast is 1,400 times 9.8. That gives me a total downward force of 17,000 newtons, which has to be balanced by the pivot point in order to keep it from falling through.